Okay, today my viewers who attend my tutorials, today I want to give a brief discussion about electrical resistivity imaging technique. In the next tutorial I will also discuss in detail about the electrical resistivity tomography. Okay, so in this program I will discuss two-dimensional electrical resistivity imaging. In the next, three-dimensional electrical resistivity imaging, and the next also four-dimensional electrical resistivity imaging. But today, since the topic is so wide that it cannot be covered by a short video, by one video, so I will give you tutorial consecutively from this onwards about electrical resistivity imaging. For this purpose, I have selected some important material from different resources, and I will use that materials and some important software for electrical resistivity survey, which is mostly used by international standard. Now let us start first some basic concepts, and we'll do examples by using the software. This software we have this software RES2D inversion software. We will see by using this software how can we generate subsurface sections, two-dimensional electrical resistivity section. I'll show you. And also, in addition to this one, we'll see about not only inversion techniques but also the forward modeling technique, or RES2D mode, or the forward modeling and inverse modeling techniques. Please attend me, you will get, I think, important concept. In addition, I'll show you about this software. This is the ABM instrument ABF. How can we use this ABM instrument AB Terameter SAS 4000 utility software, and it also used for SAS 100 utility software. I'll discuss in the future. Please subscribe, and if you get important, attend my topic and give me some important comment to improve my video tutorial. Let us start the theoretical part first. When you come to the theoretical part, let me introduce some important discussion about the resistivity survey. The basic resistivity theory. The purpose of electrical survey is to determine subsurface resistivity distribution. Subsurface of the earth, under the ground, there is a resistivity distribution, different resistivity 1, resistivity 2, resistivity 4, 5, 6, 7, which means that the subsurface has different resistivity values distributed under subsurface to the ground. When you go to deeper to the subsurface of the earth, you will get different resistivity value. When you go to laterally, there is also different resistivity values. So each resistivity value characterized by different geological parameters. So to determine subsurface resistivity distribution by making a measurement on the ground surface. From this measurement, the true resistivity of subsurface can be estimated. We have apparent resistivity and true resistivity. The objective of geophysical investigation is not to determine the apparent resistivity, but its objective is to determine the true resistivity. So its aim is to determine the true resistivity. Okay, its aim is to determine the true resistivity. This should be underlined at this point. True resistivity. Okay, true resistivity. The objective of geophysics is to determine the true resistivity, not the apparent. The apparent is only the tool or translation to get the true resistivity of subsurface. Okay, so we can estimate the true resistivity of subsurface. The ground resistivity is related to the various geological parameters. When you say the ground resistivity, this ground resistivity is not only characterized by only the geological formation type, okay, but also different geological parameters. For example, the mineral content, the fluid content, the porosity, the degree of saturation in the rock. So mineral, what type of mineral? Is it clay mineral, or it is a metal mineral, or what type of mineral, or it is semiconductor mineral, something. Okay, what type of mineral existing with the geological formation, and the fluid content. What type of fluid? Is it salty water? Is it fresh water or something? The porosity of is it highly porous? Okay, what is the percent of the porosity of the subsurface? The degree of the water saturation. Is 100% saturated by water, or 50%, 20%? Okay, these all things are important to characterize the subsurface resistivity distribution of the Earth. Okay, so when you say the true resistivity of subsurface, we mean that what are the combination within subsurface? Is there any mineral? Is there the fluid content is high or low? What type of porosity it has? The degree of saturation by water. This all be determined the true resistivity of the geophysical characteristic of subsurface. Electrical resistivity survey can be used to many decades in hydrogeological, mining, and geotechnical investigation. Okay, electrical resistivity survey has been used for many decades in hydrogeological, mining, and geotechnicals. Okay, mostly for oil investigation, mineral investigation, but later it becomes important for hydrogeological and geotechnical investigation. Okay, from its history starts from the Schlumberger brother. Okay, 1928. Okay, when you say geophysics, you know, the knowledge of physics is important. For example, you know Ohm's law. It is in physics. Ohms determines the relation between voltage drops, current, and resistance. Okay. The fundamental physical laws used in resistivity survey is Ohm's law that governs the flow of current in the ground. Okay. The fundamental physical laws used in resistivity survey is Ohm's law that governs the flow of current in the ground. The equation for Ohm's law in a vector form for the current flow in a continuous medium is given by what form? In vector form. But you know, in the lower grade we know that, okay, resistance is equals to voltage over current. Resistance is equal to voltage over current. So J is equal to this one. The current density is equals to the current, this conductivity of the medium times electrical field. Okay, this is a basic relations. It is the vector form of the current flow in the continuous medium. One, it is vector form. Second, flow in a continuous medium. So J is equals to sigma times E. That is, the current density is equal to conductivity of the medium times electrical field intensity. In practice, what measured is the electrical field potential. Okay. When you do in the field, practically when you do in the field, we measure there what is the potential drop. Okay, once we know the current, what amount of current we released into the surface, subsurface, and if you measure the potential drop or the potential field, so we can measure the resistance. If we measure the resistance, we can determine the apparent resistivity by resistance times geometrical factors will give us apparent resistivity. We know that in geophysical survey, the medium resistivity, rho, which is equal to the reciprocal of conductivity. Resistivity is equal to 1 over conductivity. They are inversely related. Is more commonly used. The relation between electrical potential and field intensity is given by, okay, the electrical potential E and the field intensity. Field intensity E is given by, this is the grad of phi. Combining 1, 1 and 1, 2, we can get instead of J, instead of E, we insert here the grad of phi. Okay, the gradient of electric potential will give us electrical intensity, so we can substitute like this one. In almost all survey, the current source are in the form of point source. In most cases, as a point, one electrode is inserted in the ground. In this case, over an element volume delta V surrounding the current source I, located X, Y, Z, the relation between the current density J and the current by day and Morrison 1979 is given by this relation. If you multiply this by the divergence, again multiply by this by divergence, so we can get that I over delta V will give us delta X minus XS, Y minus YS, Z minus ZS, and this delta is Dirac delta function. The Dirac delta function, okay, very, very important function in physics because it is the response of impulsive force. Okay, it is shooting to the infinite without thickness. Dirac delta function. So discuss actually. This is a basic equation that gives the potential distribution in the ground due to the point source. Okay, this is the basic because we substitute in J this value. Okay, so it seems complex, but it's complex because we know J is equal to minus negative conductivity to grad of phi. So the divergence of the current density is given by I over delta V times this Dirac delta function in wax, Dirac delta function in Y, Dirac delta function in Z. Okay, so substituting here, just as to this one, this will give us this one. Okay, conductivity as a function of X, Y, Z, and electric potential as a function of Y, X, Y, Z. So this will give one by Day and Morrison. Okay, as I have said, this is very important, the basic equation. This is the basic equation that gives electric potential distribution. This is electric potential distribution. Electric potential distribution. Okay. So somebody may ask you that, how can you calculate the potential distribution in the ground? The answer is by this one, these relations. Day and Morrison give these relations. This is very important part. Okay, here Day and Morrison, 1979. Okay. Okay, this is the current is located at XYZ. Delta V is, for example, this is the ground. Okay, you have assumed this electrode is here. The current flow like this. Okay, there is a potential around this one. Okay, like this one. Okay, so how can we calculate this potential distribution? The question is that, how can we calculate this potential distribution? This is given by Day and Morrison. Okay, the divergence of the current density is given by 1 over delta V, current over potential, this the volume of the potential, or the given volume. Okay, this is the volume, the element of volume. Okay, the element of volume surrounding the current. That means there is volume. If you take this one, like this one, what is the volume of this one? Assume delta V. Delta V is the volume, and this is the current I. Here is the current I flow towards subsurface. So if you take some volume element delta V, so this current divided by the volume times Dirac delta function, X shifted by S, Y shifted by YS, Z shifted by ZS will give us the divergence. Okay, this is the most important and the basic foundation of geophysics to determine the potential distribution in the ground. Okay, without this equation everything will be difficult. So a large number of techniques have been developed to solve this equation. Okay, a number of techniques have been developed to solve this equation. This is a forward modeling problem, that is to determine the potential that would be observed over a given subsurface structure. Fully analytical methods have been used for simple cases such as a sphere in homogeneous medium or vertical fault between the two areas, each with a constant resistivity. For arbitrary resistivity distribution, numerical techniques are commonly used. For 1D case, one-dimensional case, where subsurface is restricted to the number of horizontal layer, the linear filter method is used by Foyt 1970. For 2D and 3D case, the finite. Here in the one-dimensional case, 1D, Okay, linear filter method is used, but for 2D and 3D, for 2D and 3D case, finite difference or finite element method are the most versatile. We will look at this use of the forward modeling computer program for 2D structure. We will look at the use of forward modeling computer program for 2D structure. Okay. Now, to have a good conceptual mind about subsurface, instead of using inversion technique, it is better to use forward modeling techniques first. You should experience of using forward modeling techniques first, then you will go inversion technique after that. Unless and otherwise you are well acquainted and experienced with that forward modeling techniques, okay, you will not understand your mistake when you are doing inversion techniques. Okay, the more complicated case will be examined in the latter section. First, we start with simple case with homogeneous subsurface and a single point current. Homogeneous subsurface, a single point current source on the potential varies inversely with distance from the current source. The equipotential surface have hemisphere shape for a single electrode or a single current. Then the current flow is perpendicular to the equipotential surface. The potential in this case is given by here. Now here, before we proceed to the detail about two-dimensional, let us have a well understanding about one-dimensional, which means we have subsurface here and we have electrode, one current electrode. Assume a single electrode current. The current flow like this one in different direction, like this. Okay. Okay. This is only to give highlight. Okay. So you do have equipotential surface like this one. That's perpendicular to what? Equipotential surface perpendicular to the direction of the current. Here, the direction of the current and the potential is 90 degrees. Okay. So the potential phi is equal to rho times I over 2 pi r. Phi is potential, okay, for a single. So resistivity times electrical current over 2 pi r will give us the potential. R is the distance of the point in the medium, including the ground surface. The distance of the point in the medium, including the ground surface, from the electrode points. In practice, all resistivity survey use at least two current electrodes, a positive current and a negative current. We have two. In practice, two electrodes. We use two electrodes, so the calculation will be, but for single electrode, phi is equal to rho I over 2 pi r. Okay. The potential distribution caused by a pair of electrodes. The potential value have asymmetrical patterns about the vertical place at the midpoint between the two electrodes, and the potential value in the medium from such a pair is given by, okay, we can see from the figure 1.2 shown. Let us see 1.2. Okay, this I think figure 1.1, this one. Here is a single electrode. Here is the direction of the current as this one, and here is the equipotential surface. Equipotential surface. Okay. Now the direction of the current and the equipotential surface is perpendicular to each other. There is 90 degrees here. Okay. If you go every point it is a tangent of the curvature and the line makes 90 degrees. This is the direction of the current flow. This is equipotential surfaces. For a single electrode, the flow of the current from a point source and the resulting potential distribution. Okay, here one point, the potential distribution caused by a pair of current electrodes 1 meter apart with a current of 1 ampere and homogeneous half surface with resistivity 1 ohm. Now this section is plotted by using, we have only a single electrode, the current flow radially outward from the electrode, and the potential is not disturbed, it is hemispherical and it's perpendicular with the current flow. But instead of one, if you have used two electrodes, C1 and C2, you know, there is what? Stretching of the potential, and here the distribution of the equipotential surface is changed. That means the distance between each equipotential surface will be smaller and smaller. One to the other will be nearer and nearer when the two electrodes, between the two electrodes, but its farther will be large when out from the electrodes to the both sides of electrode. But between them, the equipotential surface will be what? Compressed. Okay. Now, for example, if you take this is experimental result, the potential distribution caused a pair of electrodes, C1 and C2, 1 meter apart. The distance between the two is 1 meter. From this negative 0.5, 0.5. The distance between the two is 1 meter apart, with a current 1 ampere is flowing. Okay, the current flow 1 ampere, and homogeneous half space with the resistivity 1. That is, the resistivity of this medium is the same type of material or geological formation with the same saturation level, porosity, mineralization. Okay, all things are the same, and the measurement of resistivity value is 1 ohm. So when you see the distribution of the equipotential is not the same as that of a single electrode, but when there is two electrodes, there is the equipotential surface will be compressed, okay, between the two electrodes, and the distance between each equipotential will be nearer to one to the others. Okay, that is, there is a deformation. So as I have said, the potential is equal to rho I over 2 pi r. So for the two electrodes C1 and C2, the potential rho I over 2 pi r over, instead of r, 1 over C1 minus 1 over C2, because the current one is negative, so it will be minus here. When I add up the potential by C1, the potential contribute by each electrode here is single here. The potential at any point is given by rho I over 2 pi r. Okay, r is the distance from the point to the electrode distance, the current source. But here, at any point, if you take, for example, here, the distance from this one is R1, is RC1, and the distance from this one to this one, for example, RC2. So the potential at this point is the summation of the potential by C1, contributed by C1 and C2. So this one, for example, it's positive, assume it is positive, and here is negative, so the summation will be the potential contributed by C1 minus potential contributed by C2. Okay, so that C1 and C2 are a distance of the point from the first and the second current electrode. In practical all survey, the potential difference between the 2 points normally on the ground surface is measured. In practice, all survey, the potential difference between the 2 points normally on the ground surface is measured. A typical arrangement with 4 electrodes is shown in the figure 1.3. The potential is, for example, practically we measure R1, C1, R1, C2 on the surface, not within the ground. Okay, so the arrangement may be like this one. Okay, this is the most conventional array with 4 electrodes to measure the subsurface. C1, P1, P2, C2. C1 is current, C2 is current. P1 and P2 are potential. So 4 electrodes are arranged like this one. Okay. So what happened? So the contribution, the total potential drop is at 2 points. One, the potential 1 C1 has potential at this P1, and C1 has a potential P2, and C2 has a potential at P1, and C2 has a potential at P2. So when you calculate this one, we can get this value, okay, from C1 minus 1 C2 P1, okay, minus C1 P2 plus 1 over R C2 P2. Okay, the above equation given the potential that will be measured over the homogeneous half space with 4 electrode arrays. Actual field survey are invariably conducted over inhomogeneous medium where subsurface resistivity has 3D distributions. Okay, the above given potential that will be measured over homogeneous half space with 4 electrodes. This is for homogeneous. Actual field surveys are invariably conducted over inhomogeneous. Our assumption is homogeneous, but the reality is inhomogeneous medium where subsurface resistivity has 3D distribution. Okay, the resistivity measurements are still made by injecting current into the ground through the 2 electrodes C1 and C2 and measured the resulting voltage difference between P1 and P2. From the current I and the potential delta phi value, the apparent resistivity rho A value is calculated on this one. Okay. Because this is resistance, okay, potential difference over current resistance, so geometric factor times resistance will give us apparent resistivity. So the resistivity is given by geometrical factor K times resistance value. This resistance value is what? This resistance value is given by what? Delta phi over I. Okay. So one can calculate the geometrical factor as 2 pi over this value. Okay, we know K is geometrical factor that depends on the arrangement of the 4 electrode resistivity measuring summation normally given by R is given by delta phi over I. This is the geometrical factors. In practice, apparent resistivity is calculated by this one, geometrical factor times resistance, give our resistivity. The calculated resistivity value is not the true resistivity of the subsurface. It is not true resistivity, okay, but an apparent. It is a calculated value that resistive homogeneous ground. It is a resistive. What is apparent resistivity? It is a resistivity of homogeneous ground. If the ground is homogeneous, true resistivity and apparent resistivity is the same. Will be given the same resistance value for the same electron arrangement. The relation between the apparent resistivity and true resistivity is a complex relation. It is complex relation. The relation between the apparent resistivity here and the true resistivity is a complex relation. To determine the true subsurface resistivity from the apparent resistive value is inversion problem. We call it inversion problem. To get true resistivity from the apparent resistivity, the method is known as inversion problem. Method to carry out such inversion will be discussed in more detail at the end of this chapter. Figure 1.4 shows the common arrays used in resistivity survey together with their geometrical factor. In their later section, we will examine the advantage and the disadvantage of each one. Okay, some of these arrays. There are two more electrical based methods that are closely related to resistivity method. There are two more electrical based methods that are closely related to resistivity methods. These are induced polarization method and spectral induced polarization method, SIP, also known as complex resistivity, CR, complex resistivity method. Both methods require measuring instruments that are more sensitive than the normal resistivity method, more sensitive. Okay, induced polarization and spectral induced polarization plus in front of induced polarization IP we add spectral, so spectral induced polarization and induced polarization. Sometimes it's called complex resistivity. It requires both SIP and IP requires more sensitive instrument than the normal resistivity method, as well as significant higher current. The amount of current is higher for IP method. IP survey are comparatively more common, particularly in mineral exploration. In mineral exploration, we use IP survey. It's also to detect conductivity mineral of very low survey are comparatively rare. It is able to detect conductive minerals of very low concentration that might otherwise be missed by resistivity or electromagnetic survey. It is detect conductive mineral of very low concentration. Okay, that might otherwise be missed by resistivity or electromagnetic survey. So IP is very important in mineral exploration because it is sensitive for low concentration, even for the low concentration. Commercial SIP survey are comparatively rare, although it is rare. Also, it's popular research subject. Both IP and SIP surveys used alternative current in frequency domain. Of much higher frequency than standard resistivity. Okay, the frequency of IP and the SIP is okay, much higher than standard resistive survey. Electromagnetic coupling is a serious problem in both methods. To minimize electromagnetic coupling, dipole-dipole or dipole array is commonly used. Why do you use dipole-dipole or pole-dipole array? Because to minimize electromagnetic coupling. That means the potential and the current electrode will be what? Will be what? Interfere one to the others. Okay, so the current may flow through the potential wire by coupling effect. Okay, so this is the risk. Okay, let us see some common known winner alpha, winner beta, winner gamma, pole-pole, dipole-pole, pole-dipole, winner Schlumberger, combining winner and Schlumberger, equatorial dipole-dipole, okay, and their geometrical factor is given for each of. Okay, a common array that is in resistivity survey and their geometrical factor. Note that the pole-dipole, winner Schlumberger arrays have two parameters: the dipole length A and the dipole separation N, while N factor is commonly an integer value. Non-integer value can be used. Here AA, but dipole A and N times A, N times A, N times A. Okay, you can study by yourself this actually, the electrical property of material. Okay, let us discuss about the electrical property of Zer's material. Okay. Okay, I'm inviting you one music song, spiritual song. It is a Protestant song from Ethiopia, Amharic language. I invite you this one for your spiritual revival. To relax yourself before I proceed to the next discussion about the electrical properties of the mineral. Please enjoy it now. This music says that Jesus does not forget his sons and daughters like a man. He will not let you alone. He is with you. He always helps you. This guy is deeply contacting God or Jesus in a spiritual way. This all teenagers, younger souls are feeling good, worshipping their God. This is amazing how the pupils are indulged and immersed in spiritual realm. How strong is teaching of Jesus Christ still now, from 2000 years ago till now, in this modern time, how influential his teaching is now. Many teachings become obsolete today, but Jesus' teaching becomes fresh today. How he touches the heart of the pupil. These people are not rich people in economical aspects. Still, they are living in under poverty country like Ethiopia, but they are amazingly happy and intelligent in spiritual world. They are touching their God in spiritual manner. This is a great thing, like a geophysics. We are striving to investigate subsurface of the land, this complex. But the more complex part of human being is his heart. Enjoy and listen how these people are getting their Jesus Christ in their heart. Okay, thank you. Let us proceed. I think you got this amazing video, huh? Interesting. How pupils seek their gods. How the pupils would like to enjoy in spiritual realms. Now let us also enjoy geophysics now, and let us indulge like this one for geophysics. Okay, electrical property of the materials. The electrical current flow in the earth material at shallow depths through the two main methods. They are electrode conduction and electrolytic conduction. Okay, electrical current flow in earth material at shallow depths through two main methods. They are electronic conduction and electrolytic conduction. Okay, mostly we know that electronic conduction, but we are not mostly aware of about electrolytic conduction. In this topic we'll discuss about how electrolytic conduction works in subsurface of the earth. In electronic conduction, the current flow is via of free electrons such as metals. In electrolytic conduction, the current flow is via of the movement of ions in the ground. In environmental and engineering survey, electrolytic conduction is probably the more common mechanisms. Electronic conduction is important when conductive minerals are present, such as metallic sulfide or graphite in mineral survey. Here we should understand that both are important. Electronic conduction and electrolytic conduction are important investigation for subsurface layers, but mostly we use electrolytic conduction, especially when we are investigating groundwater and especially when there is ions in the groundwater. Okay. But in environmental engineering, electrolytic condition is probably the more common. Environmental and engineering survey, it is probably. Electronic conduction is important when conductive mineral is present, such as metal sulfide, graphite. Okay, survey. The resistivity of common rocks, soil, material, and chemical. Okay, resistivity of common rock, soil, material, and chemical. Okay, by Killers, Kinchets, Daniels, Alberti, Telford, is shown in the figure 1.5. Igneous and metamorphic rock typically have high resistivity value. The resistivity of these rocks is greatly depends on the degree of fracture. Percentage of fracture filled with water. The percentage of fracture filled with water. This a given rock types and have a large range of resistivity from about 1,000 to 10 million ohm meter, depending on whether it is wet or dry. The characteristics is useful in the detection of fracture zone and other weathering features such as engineering and groundwater survey. Sedimentary rock, which are usually more porous and have higher water content, normally have lower resistivity value compared to igneous and metamorphic rocks. Sedimentary rock, which are usually more porous and have higher water content, normally have lower resistivity value compared to igneous and metamorphic rock. Sedimentary rock, which are more porous and have higher water content, normally have low resistivity value compared to igneous and metamorphic rock, and the resistivity value ranges from 10 to 10,000. Okay, 10,000. 1, 2, 3, 4. Okay, 10,000 ohm, with most value below 1,000 ohm meters. And the resistivity value are largely dependent on the porosity of the rock and the salinity of the contaminated rock. Unconsolidated sediments is generally have even lower resistivity values than sedimentary rock, with value ranging from 10 to 1,000 ohm. The resistivity value depends on porosity, assuming that the pores are saturated, and as well as the clay's content. Clayey soil normally have lower resistivity value than sandy soil. However, note the overlapping resistivity value of the different class of rock and mineral. This is because the resistivity of particular rock or soil sample depends on the number of factors such as the porosity, the degree of water saturation, the concentration of dissolved minerals. Resistivity of groundwater vary from 10 to 100. The resistivity of groundwater from 10 to 100 ohm, depending on the concentration of dissolved salt. Note that low resistivity about 0.0 ohm meter of seawater due to the relatively high salt content. This makes the resistivity method an ideal technique for mapping saline and freshwater interference in coastal area. Okay, saline water and freshwater interference in the coastal area. one simple equation that gives the relation between the resistivity of porous rock and fluid saturation factor is RES law. It is applicable for certain type of rock and sediments, particularly those that have low clay content. The electrical conduction is assumed to be through the fluid filling pores of the rock. RES law states that resistivity of the rock is equal to A times resistivity to water times phi fraction of the rock filled with water fraction raised by minus m. And m are two empirical parameters by Keeler and Fichette 1944. A rock A is 1 for most rock. A is 1, M is 2. Here is 1 for most rock. A is 1 for and M is 2. For sedimentary with a significant clay content, other more complex equations have been proposed by Oliver. Okay, so resistivity of the rock is given by resistivity of water times the fraction of the rock filled with the fluid raised by 2. If it's 100%, it's 1. Phi will be 1. If it's 50%, 0.5. So depends on that. So the resistivity of several types of ores are also known. Metallic sulfides such as pyrrhotite, galena, pyrite have been typically low resistivity value of less than 1 ohmmeter. Note that the resistivity value of a particular ore body can be differ greatly from the resistivity of individual crystal. Other factors such as the nature of the ore body, mass or be disseminated have significant effect. Note the graphite slates have a low resistivity value similar to a metallic sulfide, which can give rise to problem in mineral survey. Most oxides, such as hematites, do not have significant low resistivity value. One of the exceptions is magnetites. The resistivity value of several industrial contamination are shown in the figure 1.5. Metals such as iron have extremely low resistivity value. Chemicals that are strongly electrolytes such as potassium chloride, sodium chloride can greatly reduce the resistivity of the ground of water to less than 1 ohm, even at fairly low concentration. The effect of the weak electrolytes such as acetic acid is comparatively smaller. Hydrocarbons such as xylene typically have very high resistivity value. However, in practice, the percentage of hydrocarbons in a rock or soil is usually quite small and might not have a significant effect on the bulk of resistivity. As an example, oil sand in the figure 1.5 is the same range of resistivity value as alluvium, resistivity rock and soil of minerals. Okay, you can study this one and I can show you this one. You can see from the video and you can take time and study it. Okay, I will proceed. One-dimensional resistivity survey and inversion, application, limitation and pitfalls. The resistivity method has origins in 1920 due to the work of the Schlumberger brothers. For example, for approximately the next 60 years, for the quantitative interpretation, conventional sounding survey of cofoid will be normally used. In this method, the center point of the electrode array remains fixed, but the spacing between the electrode is increasing to obtain the information about the deeper section of the subsurface. Okay.
ሌላ ቦታ ነው ያለው አይ እዚሁ ነው
እዚህ ያለ ግን
ፈቃዱ ለሃለ እና ከሷ ጋር ነው ነገሩ ማመቻቸት
መጣለች ግን ከተወሰነ ሰዓት ከዚህ አካባቢ ከሆናችሁ ልደት ጋር ሄዳ ነው ልጆች ጋር በቃ እንደዛ ነው። Okay. Okay. Sorry, somebody has called me. And excuse me, this video is too long to be continuous without an interruption. But since it is education, don't worry. Okay, the resist method has its origin in 19 seconds due to the works of the Schlumberger brothers for approximately the next 60 years for quantitative interpretation. Conventional sounding cofoid 1979 were normally used. In this method, the center point of the electrode array remains fixed, but spacing between the electrode is increased to obtain more information about the deeper section of subsurface. The measured apparent resistivity value are normally plotted on the log paper. To interpret the data from such survey, it is normally assumed the subsurface consists of horizontal layers. In this case, subsurface resistivity change only with depth. Okay. That means the center is fixed. And the spacing between electrodes increase. To get more information about the deeper section of subsurface. To measure the apparent resistivity values are normally plotted on the log paper. To interpret the data from such survey, it is normally assumed that the subsurface consists of horizontal layer. In this case, the subsurface resistivity change only with depth, but not change in horizontal. Okay, in the sounding, we assume that the variation only with depth, not on the horizontal direction. A one-dimensional model of the subsurface is used to interpret measurements. Figure shows example the data from the sounding survey and possible interpretation of the model. This method has given useful result of geological situations such as water table, where one-dimensional model is approximately. Software provide RES2DINV.exe. Okay, 1D.exe is simply inversion and forward modeling program of 1D model that consists of horizontal layers. Besides the normal resistivity survey, the program will enable you to model IP as well as SIP. Okay. Okay, here is one-dimensional, here is two-dimensional model, here is three-dimensional model. In the dimensional model, you know that the horizontal, there is no variation horizontally, same along this line, all are row 1, row 2, row 3, only the variation of the resistive with depths. Two model, you can have resistivity difference downward row 1 to row 2 or horizontally row 1, row 2, row 3. Okay. In three-dimensional, the variation will be downward horizontally into the deeper part of the layer, like a box. Okay, like a box here. So there is RES1D inversion software that can be used to interpret RES1D inversion software. Okay. I'll show you this one if you like it, but my aim here is to show you about the electrical resistivity technique. Okay, so we'll see about the two-dimensional electrical resistivity. This RES1D is like a winner method. You can refer my previous video, winner resist method. If you go to YouTube and refer winner resist method, you can get one-dimensional about the one-dimensional method. About if you go to this video, winner resist method, winner resist, you write this one in the video, so you can see how one-dimensional will be work. Okay, and I'll show you in another time. If you want this RES1D, you can write in comment. I'll show you. This is RES1D, resistivity one-dimensional by software. This software used for one-dimensional model for inverse and forward modeling. Software for teaching purposes, actually not normally used for this, normally used for practical field work. Okay, the greatest limitation of resistivity sounding method is that it does not take into account the lateral change. This is a limitation, lateral change. Such changes are probably the rule rather than exception. The familiarity include the effect of such lateral changes can result error in interpreting the layer resistivity and or the thickness. As example, show 2,4D model where the main structure of the two-layer model with resistivity 10 ohm and thickness of 5 meters for the upper layers while the low resistivity is 1 ohm. Adding the upper layer to the simulate latter homogeneity, the 2D model has 144 electrodes that are 1 meter apart. The apparent resistivity pseudo section for the Wiener-Schlumberger array are also shown. For the Schlumberger array, space between the potential electrode is fixed 1 meter. For the apparent resistivity, the Wiener-Schlumberger array sounding survey. Okay, this will be shown here. This is a two-dimensional resistivity by Wiener array. Okay, there are different arrays actually. Here Schlumberger array. Okay, 2D resistivity model. Now with different here, look, to understand and interpret subsurface layers by using two-dimensional method. For example, if you have given this type of model and there is one anomaly body here, a 2D two layers model with a low resistivity prism in the upper, and calculate the apparent resistivity restriction for A Wiener and B Schlumberger. The 2D model, the midpoint of conventional sounding survey is shown. Now you have given the resistivity value here. Here is 10. This is 1 and 100. Okay, this conductive body is embedded in 10 ohm and underlain by 100 ohm. If you conduct Wiener or Schlumberger array method, the response will be like this one. Okay, now this anomaly part will be observed here, look here and here, but it's not exactly the same as the true model like this one. For example, here is a rectangle, for example, but it is not really rectangle but approximate to rectangle. Okay, the value of this one is 1 ohm. 1 ohm means here is 5 ohm, 3 ohm, 2 ohm. Here is around this one. Here around this one. Now, so if you look in both methods, they do not have exactly the same response. For example, if you take to the left part, they are almost similar, approximately okay, similar here, but when you come to the anomalous body, somehow they are different. They are affected by, more affected by what? Schlumberger is affected more. It shows different resistivity value, but actually there is no different values here, only one value. Okay, this one also follows the trends, so that when you see the zero section, actually here is a zero section of Wiener and Schlumberger. For this model, it is somewhat similar and different, similar in out of the anomalies, but different in anomalies at the low section. Okay, so interpretation is not a simple task. Take care of interpretation. Is about the basic theory. Okay, it will be tedious if I continue like this one, so let me show you for today about RES2DINV, one example. Let me show you one model. For example, let me show you For example, let me show you diag. There is a diag completing reading of the data and was this one. Okay, now once I read the data, model name is blocks, number of electrodes 60, number of apparent resistivity value 16, number of apparent value resistive level is 16, number of water layer, electrode spacing 5 meter, no remote electrode, model of grid depicted, okay, and the depth of the value for the row is given here. So after that, calculate the potential value. Okay, this is the potential resistivity value versus this one. Okay, now calculate the 2D resistivity section. Use input surface array, use input borehole array, use radial parameters. Okay, which one? Okay, so okay, let me give a name. So let me say okay. Look. So that I have given the model and we can generate the data. Okay, given the model and we can generate 2D sections from the model. This is a model given. So from this model I can generate 2D section like this one. Okay. Okay. Model computation. Calculate apparent for non-standard case. So we can generate it like this one. There is inversion techniques, two-dimensional inversion. We can open RES2DINV inversion like this one, and we can open data. For example, let me select one data. For example, winner 32. Read the data complete. Okay, then from this, once I read the data, I'll go to inversion techniques. So let me do this inversion techniques. Okay, by Jacobian method and by using finite difference modeling and finite element, okay, the inversion will be successfully accomplished. Okay, and we can get three things at the same time: the zero section, measuring apparent resistivity zero section, okay, calculated apparent resistivity zero section, two zero section, that is the measured apparent resistivity, calculated apparent resistivity, and inversely modeled resistivity sections. So when you conduct two-dimensional resistivity technique by using RES2D inversion software, okay, the three displayed value are the first one, this one, measuring apparent resistivity pseudo section, calculated apparent resistivity pseudo section, inversion model of resistivity pseudo section. Okay, this is a field measured value, and when it's plotted by pseudo section technique, and this is the calculated of the true resistivity, the calculated resistivity value, which is expected to approach to the model, the true model resistivity value. Okay, gives this pseudo section, and this is the true resistivity value. Okay, so that if you look the pseudo section value, the maximum is, even there is not a lower yellow color, there is not red color, but there is red color in the true resistivity. So apparent resistivity value is very low compared to, it is below 13. Okay, whereas the true resistivity can have a value greater than 50. So you should not interpret by using pseudo section, but only pseudo section shows the quality of the data as well as the direction of the high resistivity value and the low resistivity. It shows the direction and the quality, not the value. But the true resistivity values shows or estimates the high resistivity anomaly in particular points and the low resistivity value in particular points clearly. So it's important to use, okay, these pseudo sections and the inversion model resistivity value. Okay guys, today it is enough. I'll proceed in the next time in more detail. If you subscribe, you will get my video in the next time. Thank you for your attention, and please enjoy geophysics. It is very important subject for economical development as well as mental satisfaction. Bye bye.